the question on radioactivity. So it says, start, half-life of a radioactive sample, strontium 9038 is 28 years. So half-life of, we represent it as T half is equal to 28 years. Strontium, okay. Calculate the rate of disintegration. So the rate of disintegration is nothing but activity. Disintegration per second is activity. So I call it as A. Rate of disintegration of 15 milligram of this isotope. So mass 15. So let us keep it in grams. So 10 to the power minus 3 grams. And also the number of atoms in terms of Avogadro number, simply Avogadro number 6.023 into 10 to the power 23. So what we need to find out? We need to find out the activity. So in order, what we have the formula is activity is equal to lambda n. So here we need to calculate both the values. One is lambda. It can be calculated using the half-life period, and the other one is number of atoms in the given sample. Number of atoms in the given sample. So let's find out first this one. Lambda is equal to 0.693 into 28 years. So let's convert into seconds. That is 28 into 365 into 60. Okay, 24 into 60 into 60. So let's find it out. 28, 365, 24, 60, 60. So this is going to be 0.693 whole divided by 369. So I can write it as 1.5 into 10 to the power 9. 1.5 to 10 to the power 9. So 0.693 divided by 1.5 is coming out to be 0.462 into 10 to the power minus 9. So we got the value of lambda as 0.462 into 10 to the power minus 9. So we got lambda. Now we need to find out the number of atoms in the given sample. Number of atoms in the given sample that can be found. N is equal to given mass divided by the atomic mass. Atomic mass, that is given mass, I simply write it as mass multiplied by Avogadro number. So given mass is 50 into 10 to the power minus 3 and Avogadro number 6.023 into 10 to the power 23 whole divided by the atomic mass is 90. So let's solve this. 15 multiplied by 6.023, that is 90.345 into 10 to the power 20 whole divided by 90. So it has 1.0038 into 10 to the power 20 atoms in the given mass. So we got the number of atoms and also we have the value of lambda. So then we can able to find out the activity, that is rate of disintegration. So that is A is equal to lambda n. So lambda is 0.693 power minus 9. So this is 1.0038 into 10 to the power 20. So we get it as 0.463 or 464, we can round it off, into 10 to the power 11. Minus 9 plus 20, 11, or you can write as 4.64 into 10 to the power 10 disintegration per second. Disintegration per second, or you can write becquerel. So here we can stop. If they ask us to calculate the disintegration, rate of disintegration in curie, so the next step can be 3.7 divided by 10 to the power 10. So you can also write that one in curies also. So a very simple numerical. They are asking us to calculate the rate of disintegration, that is radioactivity. The given is half-life and the mass. So activity is equal to lambda, that is decay constant, into number of atoms. So decay constants can be found by half-life and number of atoms can be found using the formula mass divided by atomic mass multiplied by Avogadro number. It's a standard one. So finally we can able to calculate the activity. Let's move on to the next question. The next question, question number 11, which is asked in March 2019 from unit 9 and 10. This question is from nuclear, which is similar to the question what we have solved earlier. So it says half-life of uranium-238 undergoing a decay is half-life, that is T half is equal to 4.5 into 10 to the power 9 years. Later we will convert it into seconds. What is the activity of 1 gram of, so the mass is given 1 gram of uranium-238. So atomic mass we need 238. So we need to calculate activity. A is equal to question mark. So activity is equal to lambda n, that is disintegration per second, is equal to decay constant into number of atoms. Let's find out this lambda, which is given as 0.693 divided by half-life. So 0.693 divided by 4.5 into 10 to the power 9 into year means 365 days, 24 hours, 16 to 60. Okay. So let's calculate this. Okay, we get this one as 0.693 whole divided by 1.42 into 10 to the power 8. 10 to the power 8. So on solving this, 0.693 divided by 1.42, we get as 0.488 into 10 to the power minus 8. So this is lambda. So we got the value of lambda. Let's proceed for the next one. N, that is number of atoms. So N is equal to mass, given mass whole divided by atomic mass and multiplied by Avogadro number. So this is 1, atomic mass is 238 into 6.023 into 10 to the power 23. This is 6.023 divided by 238. So we get it as 0.0253 into 10 to the power 23. So we got the value of n. You can also convert this one 1 to 2.53 into 10 to the power 21. You can do that. Let it be. Final value we need is activity. So activity is equal to 0.488 into 10 to the power minus 8 into 0.0253 into 10 to the power 23. Okay. So this value is multiplied by 0.488. So we get as 0.101234. Let us make it as round it up to 1235 into 10 to the power 15. 10 to the power 15. So else we can make it as 1.235 into 10 to the power 13 disintegration per second Beck per annum. So this is the value of activity. So similar method, half-life is given, the mass of the sample is given, so we need to calculate the activity. Let's move on to the next question. This is from again Nucleic chapter. Let's solve this. A very simple one. We have already solved this type of numerical in terms of nitrogen or oxygen. Let's solve it. Calculate the binding energy of alpha particle in mega electron volt. So, binding energy of alpha particle we need to find out. That is in mega electron volt. From the following data, the mass of helium nucleus, alpha particle, helium nucleus, that's it. So, right, mass of helium is 4.00260 U, and the other information, mass of neutron, that is M, N 1.00866 U, mass of proton 1.0087825 U. So it's a very simple one level. Binding energy is equal to delta M into C square. So by finding out delta M, that is mass defect, we can able to find out the binding energy. So delta M is equal to ZMB plus A minus Z Mn minus the actual mass. ZMB plus A minus Zmn is mass of the constituent minus the actual mass. That is alpha particle helium nucleus 4.00260 U. So let's solve this. Z, that is number of protons. Number of protons is going to be 2. Mp, the mass of proton, that is 1.007825 plus A minus Z, that is number of neutrons. Again 4 minus 2, that is 2 into mass of neutron 1.00866 minus M, that is 4.00260 U. So let's solve this. So we get 2.01565 plus 2.017324 minus 4.00260. Okay. Minus, I'm solving this, we get 0.0303. This is in terms of atomic mass unit, delta M. Okay. So let's find out the binding energy, delta M into C square, and we need to we must, that is 1 atomic mass unit is equal to 931.5 mega electron volt by C square. So many times in the same unit videos we have discussed this one. 1 atomic mass unit is equal to, in terms of mega electron volt. So we have this. Then binding energy, so 0.0303 into 931.5 mega electron volt divided by C square and multiplied by C square. This is entirely mass defect and C square. So here we get C square and C square gets cancelled. This is multiplied by 931.5. So we get 28.29 mega electron volt. So this is the binding energy of R4 particle in mega electron volts. So this is question number 12. I think this is asked in June 2019. June 2019. Let's move on to the next question. So we are at the last numerical from the unit 9 and 10. This numerical is also from Nucleic. This question is asked in March 2020. So why I said last numerical? Because the 14th numerical, that is supplementary exam, happened in September 2020. The question is same as June 2019, that is question number 12, but we have already discussed. So same one, that's why I am not going to discuss that. So question number 30, asked in March 2020, is a bit lengthy one, but easy numerical. Let's start with this. A copper coin has mass of 63 grams. Okay, given mass I take it as 63 grams. So calculate the nuclear energy. Follow this. Calculate the nuclear energy that would be required to separate all the neutrons and protons from each other. So the nuclear energy that would be required to separate all the neutrons and protons, which is nothing but binding energy. So we need to calculate binding energy. So binding energy is defined as the amount of energy required to separate all the neutrons and protons or nucleons. The coin is entirely made up of copper atoms. So the mass of copper is, the given mass copper is 62.92960 U, and the other values are mass of proton, mass of neutron, and the Avogadro number. Okay, binding energy, as we know, binding energy is delta M into C square. So we will find out delta M, that's done with the binding energy. So here one extra thing we need to do is, earlier we were calculating binding energy for one atom, for one given atom. Let us say alpha particle, oxygen case, nitrogen case, one atom. But here the given mass, so the copper coin, here we have a copper coin, the mass of the copper coin is 63 grams. It's not single one, it is of 63 grams. So what we need to do is, we need to find out the number of atoms present in 63 grams of copper coin. Then we multiply the binding energy with that one. So we get the binding energy required to separate all the protons and neutrons of a copper coin of mass 63 grams. So first what we need to do? We need to find out the number of atoms. How? That is, N is equal to given mass 63 by atomic mass. Okay, one more step. Given mass M, atomic mass into Avogadro number. So we get this 63 divided by 63, which is multiplied by 6.023 into 10 to the power 23. So we get 63 and 63 gets cancelled. So the number of atoms in the given mass is 6.023 into 10 to the power 23 atoms. So we get the number of atoms. Let's find out the binding energy for one atom, then multiply this total number of atoms. So let's see. Binding energy, to calculate binding energy, okay, do it directly. Delta M, that is ZMP plus A minus ZMN minus M into C square. That's all this. ZMP, Z 29, the mass of proton, here we have 1.00727 plus A minus Z, that is 63 minus 29, so it's going to be 34. So 34, that is number of neutrons. Yes. Yeah, 34, that is number of neutrons. The mass of neutron is given. It is 1.00866 minus the total mass of copper is the actual mass 62.92960. So let's solve this. 29 multiplied by 1.00727, this is coming out to be 29.21083 plus 34 into 1.00866. So this is coming out to be 34.2924 minus 62.92960. So that's all this. So get the value 0.57567. Of course, C square we have. This is U and C square. 0.57567 into 931.5 mega electron volt divided by C square multiplied by C square. So we get the final value as the binding energy as 536.236 mega electron volt. C square gets cancelled out. So what else we need to find out? This is the binding energy of one atom of copper. But the mass, given mass has this amount of atoms. So the total binding energy will be this value multiplied by this value, number of atoms, that is, I write here total binding energy is equal to 536.236 mega electron volt into 6.023 into 10 to the power 23. So whole divided by, sorry, we get the final value 3229.75 into 10 to the power 23 mega electron volt. So this is the total binding energy required to separate all the protons and neutrons in the given mass of copper. So this completes the numericals from the unit 9 and 10. It's a very direct one, except the mass and extra factor, that is mass, is given. So we are done with this one. We will start with the new two sets of units. So let's move.